SwayamPrabha. Digital India. Educated India.
Last class we talked about the eutectoid transformation. The logical extension of that is the Martensitic transformation. Let us look at that today. As you all know, this is one such transformation where diffusion is not involved. It is a diffusionless shear transformation. When all diffusional mechanisms fail, that means you come to a temperature where diffusion is not able to happen inside the alloy. At the same time, the parent phase is not stable, so it wants to transform to something, and there is no other go but to go by some mechanism by which it can transform. That mechanism is a shear mechanism. So you see this happening in many alloy systems. The most classic alloy system is what we know, the steels, the iron carbon alloys, but you will also see not only in that the shape memory alloys, if you have heard of shape memory alloys, the basic mechanism that gives shape memory effect is the martensite. So you see the nickel titanium, people call it as nitinol, is a very classic example. Iron carbon is another example. Even in copper nickel aluminum kind of alloys or copper zinc aluminum kind of alloys, there are a number of copper based alloys where you see, for example, copper zinc also you can see martensite formation when you quench it from high temperatures. So all these are can be grouped basically into one class of transformation, which we call it as a Martensitic transformation, where you have a diffusionless shear. Diffusionless transformation, and it is a shear transformation. Let us see, many of you know it. Let us see how this shear takes place. If you look at the iron carbon example, if you see the parent phase that is undergoing the transformation is the austenite. It is the austenite which gives you martensite. In fact, in the last class also we have talked about it. If the austenite, the cooling rate is such that the austenite already gives you the perlite, or maybe you have cooled it to a temperature where you have held it for a long time to get a bainite. So under such conditions, how do you get martensite? We said the only way to get martensite from a bainite or from a perlite is to take it back to the austenization temperature and see that all the perlite and all the bainite get transformed to austenite, and then transformation to martensite is possible. The reason is that you know that it is only one structure transforming to another structure by a shear, whereas if you consider perlite or bainite are two phase mixtures. So it is not possible for a two phase mixture to shear to give you a one single phase. So whenever we are talking about a shear transformation, it is one structure where you have a shear along a particular direction taking place to give you a martensite. So if you look at that, if you look at this, what you see is in principle, if you start thinking of lattice points here and then extend this to one more unit cell like this, and look at these two unit cells together, and if the unit cell is a face centered cubic, that means you have a lattice point here, you have a lattice point here, you have a lattice point here, you have a lattice point here. If I join these lattice points, two of them, and if I also join this lattice point with the corner atoms or corner lattice points and join this, in principle what you have generated now is what kind of a structure unit cell is that? It is a tetragonal unit cell, and not only it's simple tetragonal, it is a BCT because there is one here. The face centered lattice point of this becomes a body centered lattice point for the body centered tetragonal. So now you have a BCT generated out of an FCC. Any FCC unit cell can be thought like this, you do not need a shear there. What is a unit cell? Unit cell is an imaginative way of representing lattice points, I mean the way atoms are arranged. I have atoms are arranged in a unit, in a 3-dimensional structure like this, and that I can visualize it as a FCC, and the same FCC can be visualized as a BCT. Then why don't I call this unit cell as a BCT, why should I call it as FCC? Every FCC unit cell can be thought as a BCT unit cell, every FCC unit cell. Why are we calling it as FCC? Why can't we call it as BCT? Have you ever thought about it at the second year BTech level when people are teaching you unit cells? Isn't it? Every FCC can be simply, I keep on joining, instead of joining this way and putting all the atoms here or the lattice points there, I join in a different way. I mean, you can have continuous. See, when I am saying joining two unit cells, there are no unit cells inside a lattice. In a 3-dimensional arrangement of atoms, there is no unit cell. It is a unit cell that you are imagining, that this is the unit cell. When the atoms, I give you a simple example. A 2-dimensional unit cell. Imagine all the atoms are of the same size, okay, it is same type of atoms, and you have a 2-dimensional unit cell. Now the question is, I can choose this as a unit cell, I can choose this as a unit cell, I can choose this as a unit cell. So I have shown you 3 possibilities. One can imagine innumerous possibilities. Which one I should choose as a unit cell?
The smallest unit which represents the 3-dimensional
symmetry. The smallest unit which represents the symmetry of the unit cell. You may say that what is the symmetry of it? How do I know? The smallest unit which has the highest symmetry among those arrangement of lattice points, which has the highest symmetry among those, and it should be the smallest. Now comes to this, if you look at all these, what is the symmetry of this, what is the symmetry of this, what is the symmetry of this? If you look at it, this has a 4-fold symmetry, am I right? This does not have a 4-fold symmetry. A rhombus cannot have a 4-fold symmetry. When will you have a 4-fold symmetry? Can you tell me, in a 2-dimensional object, okay, when will you get a 4-fold symmetry? What is the condition of the geometry which gives you a 4-fold symmetry? A should be equal to B. Yes, angle should be 90 and A should be equal to B, then only you will get 4-fold symmetry. Just because angle is 90, you will not, you need not have to get a 4-fold symmetry if A is not equal to B. That is what is a rectangle. A is not equal to B, but angle is 90 degrees. So that will give you what kind of a symmetry? A rectangle, what symmetry a rectangle has, Prerana? It is a 2-fold symmetry. This is what it has, this one. And if I now look at this particular unit cell alone, among this and this, if I compare it, this has a 2-fold symmetry. Not only that, Okay. This, the number of lattice points per unit cell, if I consider the number of lattice points per unit cell is how much there for that rectangular unit cell? How many lattice points per unit cell? 6 lattice points per unit cell. 2, 3, I am getting all kinds of numbers. Let us see, it is 2. Why it is 2? Voila. Corners,
Each corner will contribute 1/4.
1/4.
4 into 1/4.
Wonderful.
Plus center half plus half.
Half plus half. Each corner contributes 1/4. So 1/4 into 4, you will get 1. This is half, this is half. It's, we are looking at a 2-dimensional lattice now. We are not looking at a 3D lattice. So if you are looking at a 2D lattice, this is it. So it is 2, whereas this is 1. In fact, that is the reason why, if you have ever seen a face centered tetragonal, there is no face centered tetragonal. Have you ever thought why there is no face centered tetragonal? Because the moment I have a face centered tetragonal, I can draw the unit cell exactly like this, excepting that the C axis is a little longer, that is it, longer or shorter than the A and B. That is what is a tetragonal lattice is. So it will be exactly like this. Now if I join this top face center, this top face center with the 2 corners, and this top face center, this top face center, I mean bottom face centers with the 2 corners, and join like this, you will get another unit cell. So that means in a FCT I can see a BCT, every FCT I can see a BCT, every FCT I can see a BCT, and as a result we cannot say there is FCT, because FCT can be represented as a BCT, and as a result FCT does not exist. Otherwise, in principle, if you have ever really broke your head for this problem, that there are 7 crystal systems, am I right, and each crystal system can have 4 unit cells, 28 unit cells should have been there, 28 Bravais lattices should have been there, but how many Bravais lattices we have, Prerna? 14 only. Why only 14? Why not 24 28? It boils down like this, one by one you can take each unit cell and start discarding it with this kind of arguments. So FCT is not possible, FCT is not possible, FCT can be thought as a BCT. Now our question is, why FCC cannot be thought as a BCT? So if you want to remember the basic choice of a unit cell, we just now said that it should have less number of lattice points, it should be the smallest unit cell with the least number of lattice points per unit cell, and it should have the highest symmetry among all possible unit cells that you can think of. In this turns out to be that for this atomic arrangement. For some other atomic arrangement you may have something else. For this particular atomic arrangement where the atoms are equally spaced and this is equal to this, if that is the case, then this is the best unit cell. If this is not equal to this, then you may get a different unit cell. That is how orthorhombic comes into picture. The angles may be 90 degrees, but this is not equal to that. So you would see, you would have a different type of a unit cell where the A is not equal to B. Okay. So this is one. What else? There is one more when you consider unit cells. I do not know whether you have thought about it. This comes into picture mostly when you have more than one element in the picture. For example, if you have an ordered crystal structure, of simple example is sodium chloride. You have sodium atom, every sodium atom is surrounded by chlorine atoms, every chlorine atom is surrounded by sodium atoms. Now what is the unit cell if I have to consider? I do not consider the composite unit cell which has both sodium and chlorine atoms. I should consider that unit cell where only sodium atoms are considered and another unit cell where only chlorine atoms are considered, because a unit cell is always a unit cell of like atoms, of the same type of atoms. That is why whenever we talk about ordered structures, we talk about sublattices. and a superlattice. A superlattice is that which is composed of both the elements. For example, the moment this FCC unit cell or a BCC unit cell, for example, easy to understand, imagine a BCC unit cell. With one at the center. What is the example of an ordered BCC unit cell? I mean ordered unit cell based on BCC, I should not say copper, zinc, beta brass. Another example, cesium chloride, okay. So nickel aluminide, NiAl, these are all of that type. In that, the moment it becomes ordered, I know pretty well that if I am taking a copper zinc, copper occupies the, let us say, the corners, zinc occupies the body center. Now what is the unit cell? Once in all the unit cells, all the corner atoms are occupied by copper and all the body center atoms are occupied by zinc, I cannot call it any more BCC. It is no more BCC, because the body center position is not copper again, body center position is zinc, whereas body corners are copper. So we say actually there are two unit cells there, one unit cell made of copper atoms, another unit cell made of zinc atoms. What will be the unit cell of copper atom? What will be the, it is a simple cubic. What is the unit cell of zinc atoms? It is again a simple cubic. So you can see two simple cubic unit cells, two simple cubic unit cells, and displaced, each one displaced with respect to each other by a half. If you think that this unit cell, the another unit cell can be drawn like this, join all the body centers of 8 unit cells which are surrounding this, you will see that 8 body centers put together, you will get one unit cell, that would be a zinc unit cell. And zinc unit cell is, if I draw the zinc unit cell, okay, zinc unit cell is shifted with respect to the copper unit cell by a half distance. So these are two unit cells, one is copper unit cell, another is a zinc unit cell, and both are simple cubic unit cells, and put together this one is what we call it as a superlattice. These are the two sublattices, copper sublattice, zinc sublattice. We need to talk in terms of that. So that is why you should never say that copper zinc, ordered copper zinc has a BCC structure, it is wrong, it does not have a BCC structure. And in fact, because of this, I now tell you, if you start considering, we talked some time back, why ordered structures have low deformability, I said the Burgess vector changes. If I consider this unit cell, the Burgess vector in a BCC unit cell, what is the Burgess vector? 110, BCC unit cell 111, half 111, let us say, am I right? It is half of 111. So that means this is the Burgess vector, 111 direction is the closest pact, and that changes now the moment it becomes ordered, that changes to the simple cubic 110, and it is a full of it. Okay, I should not say this, I should say this, because that is the direction, Burgess vector is the direction. So this is bigger than half 111, am I right? The Burgess vector becomes longer. So you would see suddenly the moment it becomes ordered, the deformation occurs on different planes, it now starts searching for different directions where slip can easily occur, and as a result some of the directions, obviously you will never find a shorter Burgess vector once you are a superlattice. So as a result you will see the deformation becomes more difficult, and you will see many other things. Okay, come back to here. So the reason why we do not call this as a BCT is what now, based on whatever we have discussed. Why do not we call this as BCT? FCC, why do we not call it as a BCT? It is a symmetry. The symmetry of a cubic, what is the symmetry of a cubic system? 4. Did we talk about it? No. Did somebody talk about it at some stage to you? What is the symmetry of a cubic system? In fact, always you might have learnt cubic is A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. That is a very primitive way of learning, I would say. The best way to know about systems, crystal systems, is to know the symmetry of it. And in fact, then you will know when you say cubic, tetragonal, orthorhombic, why do we actually learn them in that order? It is because the symmetry decreases in that order. Cubic has the highest symmetry, triclinic has the lowest symmetry. That is why we talk about triclinic at the end, and that is why you do not see most of the elements actually occupying a triclinic system. Every element most tries to have as close packed structure as possible, as long as its electronic configuration allows it. That is why you see, if you see the whole periodic table out of some 105 elements or so, at least 80 elements, 80 to 85 elements fall into cubic or hexagonal. It could be FCC or BCC and hexagonal. So you see, these are the 3 which are the most popular, basically because they are the most close packed. I mean, not just close packed, they are the most symmetric. So if you look at cubic, what is the symmetry of cubic? 3-fold. And how many 3-folds? 4 3-folds it has. Where are these 4 3-folds? Diagonals, body diagonals. You have 8 corners, join any 2 opposite 8 corners of the 8 corners, join any 2 corners, opposite corners out of the 8 corners, you get a direction which is a 1 1 1 direction, am I right? And that 1 1 1 direction is a 3-fold direction, and because there are 8 corners, 4 such 1 1 1 directions are possible. In fact, actually how many 1 1 1 directions are there? Total 8 are there, 8 1 1 1. In fact, there are 8 1 1 1 planes, that is why we call it as a octahedral plane. 1 1 1 planes are called octahedral planes. The reason is because there are 8 of them, but we are only considering 4 here, because if I consider 1 1 1 and bar 1 bar 1 bar 1, they are exactly the same excepting that they are in a reverse direction. One is in this direction, another is in this direction. So both are fall onto each other, excepting directions are different. So they can be considered as one axis only. So out of the 8 you will see 4 pairs like that. If I take one bar 1 1 1 and it will be parallel to what? Bar 1 1 1 will be parallel to bar 1 1 1. This will be parallel to 1 bar 1 bar 1. It will be parallel to 1 bar 1 bar 1. So similarly we can see. So this and this will be considered as together, these 2 directions. They will be basically same direction opposite to each other. So like that you will see 4 sets, that is why we call them. And in addition to 4 3-fold axes, what else do you have in a cubic? There is another very important symmetry, 3 4 folds you have. You have 3 4 folds. You see every face is a square, every face is a square in a cubic. So as a result, this direction and this direction, the x y z, all the 3 directions are 4-fold axis in a cubic. So you have 3 4-fold axis and 4 3-fold axis. This is the highest symmetry that any crystal can have. That is why the moment you take cube and then pull it, what happens to the cube? It becomes tetragonal. Once it becomes tetragonal, what happens to the crystal symmetry? Now tell me. 3-fold disappears. Perfect. 3-fold completely disappears. The reason is for the 3-fold to have, okay, if I consider this plane, I will draw this second, okay, maybe we can show here itself, okay, I will not show there. If I consider this plane, this is your 111 plane, am I right? 111 plane, that is the one which has a 3-fold symmetry. What is the shape of that plane? Triangle. Okay. A triangle will have a 3-fold symmetry when all the sides are equal, when it is an equilateral triangle. If it is not an equilateral triangle, you will not have a 3-fold symmetry. In a cube, you have an equilateral, 111 plane is an equilateral triangle. In a tetragonal, 111 plane is not an equilateral triangle, because you have pulled it, this and this will be longer than this in a tetragonal, and because of which you do not have an equilateral triangle. Once you do not have an equilateral triangle, there is no 3-fold symmetry. So, all the 111 planes have completely got converted into equilateral triangles now, I mean non-equilateral triangles, isosceles triangles, they are all isosceles triangles, and once they are isosceles triangles, obviously you do not have a 3-fold. So, you do not have a 3-fold symmetry at all. The 4 3-folds that we talked about in cubic, just by pulling it by some few percent, you have changed it completely, you have vanished, I mean you have destroyed the 3-fold symmetry. Then what about 4-fold symmetry? Only the top and bottom faces are squares now. The remaining 4 faces are no more squares, because you have pulled it. The remaining 4 faces, what have they become? They have become rectangles, and rectangle cannot have a 4-fold symmetry. So, only the 0 0 1 direction, which is the c axis, that alone will have a 4-fold symmetry, and 1 0 0 and 0 1 0, they too will not have a 4-fold symmetry. So, whereas in a cubic, both the 1 0 0 and 0 1 0 and 0 0 1, all 3 of them had 4-fold symmetry. Here you will have only 1 4-fold symmetry. You see, from cubic to tetragonal, what a degradation in terms of symmetry. You simply have 1 4-fold symmetry, that is it. You may say, sir, it also has a 2-fold symmetry, because rectangles are there, 2 2-fold symmetries are there. Then why am I not talking about them? It is not contained inside the 2-fold axis. The 0 1 0 0 is a 2-fold, 0 1 0 is a 2-fold, 0 0 1 is a 4-fold. Why are these 2 contained in this? They are not contained in it. These 2 are 2 different directions which are at 90 degrees to this direction. They are not contained, but why do we not talk about it? We do not talk about it because whenever we talk about the symmetry of a unit cell, we talk about what is the highest possible symmetry of that unit cell. Because 4-fold is possible, we do not talk about 2-fold, though 2-fold does exist inside the lattice. 4-fold is possible. That is why in cubic also we say 3 4-folds. We do not actually talk about 4 3-folds. 4 3-folds are as a result of 3 4-folds. Am I right? Because A equal to B equal to C and all the angles are 90 degrees, the 3-fold is also coming in the way. So, you can see that it has 1 4-fold, and now from there if you go to orthorhombic, you will see then again there is a further degradation. There is no more 4-fold at all in orthorhombic. Why? Why there is no 4-fold? All the 6 faces are rectangles. Why? Because A is not equal to B, not equal to C. So, there is no, but all the angles are 90 degrees. Am I right? Alpha equal to beta equal to gamma equal to 90 degrees. because all the angles are 90 degrees, you have rectangles. If there is no 90 degrees, you would not even get rectangles, am I right? And because you have got rectangles, you have some symmetry. What is that symmetry in a rectangle? Twofold. You have a twofold symmetry. And so, what is the symmetry of an orthorhombic? Twofold. 3 two-folds. Like the way we said for cubic there are 3 four-folds, there are 3 two-folds, 3 mutually perpendicular two-folds, A, B, C, all the 3 are two-folds because all of them are rectangles. So, like that you would see from one to other, if you start going orthorhombic, you go to rhombohedron. How do you get rhombohedron structure? From a cubic structure. If somebody gives you a cube and asks, pull along the diagonal, once you pull along the diagonal, what happens now? All the directions, all the sides may remain equal, but angles will not be any more 90 degrees. Once the angles do not remain 90 degrees, you cannot have a two-fold symmetry, you cannot have a four-fold symmetry. So, there is no two-fold, no four-fold in a rhombohedron, because their angles are not 90 degrees. If the angle, for example, if you have this kind of a structure, there is no two-fold here. This is like a rhombus. Rhombohedron is almost an extension of this rhombus in a 3D, and this cannot have a two-fold symmetry because this angle is not 90. Am I right? What is the meaning of a two-fold symmetry? When I rotate a particular lattice point around another lattice point by 180 degrees, do I come back to another lattice point inside? That is what is a two-fold symmetry. So, that is possible only when the angles are 90 degrees. So, you will not be able to get that. So, once you do not get that, then obviously you have no two-fold, no four-fold, but you have one three-fold symmetry in rhombohedron. We can geometrically prove it, there is one three-fold symmetry. Similarly, when you go to a hexagonal, you have a six-fold symmetry there, because the basal plane has a six-fold symmetry, and at the same time the rectangular planes which are surrounding the basal plane, I mean the top and bottom basal planes are connected by 6 rectangles, am I right? So, those rectangular planes also will have a two-fold symmetry, but we do not talk about that. We say that hexagonal has a six-fold symmetry because two-fold symmetry is much less than a six-fold symmetry. But though we say six-fold symmetry is a higher symmetry than a four-fold symmetry, we do not put it above cubic, because cubic has 3 four-fold symmetries, whereas here only one of the axes has a higher symmetry than a four-fold, but the remaining axes have a lower symmetry than the cubic. That is why cubic is always above the hexagonal in terms of symmetry. So, whenever a certain element wants to choose a structure, first structure it would like to choose is cubic, and if that is not possible, it will choose something else. So, that is how it is. Then you go to monoclinic, you have 190 degrees angle. If you remember, A is not equal to B, not equal to C, beta is 90 degrees, the remaining 2 are not 90 degrees. So, because there is 190 degrees angle, you will get one two-fold symmetry. So, monoclinic has one two-fold, and then you come to triclinic, you have what is the symmetry? Zero symmetry? One fold symmetry it has, there is nothing like zero symmetry. Okay. Every one of us have a one fold symmetry. You rotate around yourself projection 360 degrees, you will be able to generate your own self once again. So, that is so every object has to have a three-fold symmetry, have a one-fold symmetry. One-fold symmetry is what we call it as trivial symmetry. It is a symmetry which is supposed to be there everywhere, because it is a 360 degree rotation. Any object, when we rotate it by 360 degrees, it comes back to itself, right. So, coming back here, sorry for all this deviation, coming back here, we say it is not BCT because cubic the same arrangement I can also think of as a FCC, and FCC has a higher symmetry than a BCT. So, I will consider these atomic arrangements as FCC rather than a BCT. Same atomic arrangements I can also, when there is a choice between two unit cells possible, I will choose that particular unit cell which has the highest symmetry, because that is one of the criterion to choose unit cells. So, that is why it is called a FCC. Now, when there is a shear that takes place, the shear actually occurs along the 110, which is the closed pack plane, closed pack direction. So, along that direction you have a shear, and once the shear takes place, the FCC permanently becomes BCT, because once the shear has taken place, it is no more FCC, it has become BCT because of the shear, not just because of the atomic arrangements, no, because of the shear that is taking place along that. If the shear would have taken by on any other plane or in any other direction, you would have got some other structure possibly, but because it occurs on the closest pack direction, in the closest pack direction, atoms are close packed there, you would see that it becomes BCT. Once it becomes FCC becomes BCT, what is the C by A ratio? 1.414, perfect. Why? You can see the C now is same as A, C of the BCT is equal to A of the FCC, am I right? Nothing is happening to this, only thing is now the A and B of the BCT are these two, and those two in the, when you compare with the original FCC structure, they are what? Half of, okay, of the phase diagonal. Phase diagonal is root 2a by 2. So, that means a by root 2. So, a of the BCT is equal to root 2 a, I am sorry, not able to write here, I will write somewhere else. So, a of BCT is equal to a by root 2 of FCC, and C of BCT is equal to A of FCC, am I right? So, if I take C by A ratio, it becomes this divided by that, that is equal to root 2. So, C by A of the BCT, am I right? After the shear, if I look at the C by A of the BCT, it is half, is actually root 2, but such a structure, BCC structure with a C by A of 1.414 is not stable at room temperature, because in the phase diagram I do not see such a structure, I do not see such a structure. So, what happens is the system, what is stable at that temperature in the phase diagram is a BCC structure. At room temperature in a iron carbon system, what is stable is a BCC structure, BCT is not stable. So, what happens is this particular structure wants to transform to a BCC structure. That is why the whole Martensitic transformation is composed of two processes. One is a shear which converts the FCC into a BCT, then another process whereby this BCT wants to get converted to BCC. What is that can convert a BCT into a BCC? If you want a BCT to become BCC, what should happen? Forget about carbon, we are talking of only structure. C axis has to shrink, and A and B have to elongate so that the C by A becomes 1. Okay. If C can shrink completely without A and B elongating, I have no problem. Ultimately I want the C should become equal to A. That means this has to shrink, this has to elongate, and these two have to elongate and this has to shrink. That is where the whole problem is in iron carbon diagram. In a iron carbon steels, if you now look at this whole structure and see where carbon atoms are sitting, you will see very interesting phenomena. Carbon atoms in FCC sit where? Octahedral sites. Let us look at what are the octahedral sites. One of the most common octahedral site in a FCC is what? Is the body centered position. Am I right? Body centered position is a octahedral site. In this, the body centered position is this. The body centered position of the FCC are these two, that is where carbon atom will sit. And what are the other octahedral positions? Edge centers. So that means this is an edge center, this is also an edge center. Am I right? This is also an edge center, this is also an edge center. I am not considering other points, I am only considering that corresponding to the BCT. So that means once the shear has happened, carbon atoms have not moved anywhere, they are where they are. That is the meaning of Martensitic transformation. If the carbon atoms can move, why will shear occur? Martensite would not have formed, it would have formed binite. If carbon atoms could have moved, it would have formed a binite. Because carbon atoms are not moving, they are where they are, exactly they will remain. Once the FCC becomes BCT, the carbon atoms are actually sitting here. These are the 4 edge centers, I mean these 2 body centers. If you want, I will differentiate the body centers from the edge center. These are the 2 body centers and the remaining 4 that I have put are the edge centers. Now if you look at it, out of the 6 positions of the carbon atoms, are there any other positions possible for the carbon atom in this particular unit cell? No, that is it. Those are the edge centers, those are the body centers. Once you consider that out of all these 6 positions, 4 of them are at C by 2 positions of the BCT. Am I right? They are at the center of the C axis, 4 of them. And because carbon is sitting at the center of the C axis, for the C to shrink is not easy. C cannot shrink now, because carbon is sitting there, it cannot shrink, and because it cannot shrink, BCT cannot become a BCC. That is why whenever you look at a Martensitic transformation, in fact if you carefully observe a typical martensite like a 0.8% carbon steel martensite, what is the C by A ratio in that martensite? 1.6, 1.6. You have zapped me. The maximum possible is this. When a FCC shears, this is what is the maximum, you cannot have beyond that, and the actual martensite will not have that. Go back to any of your physical metallurgy books, look at the C by A ratio, and we always say C by A ratio increases with increasing carbon content. If you remember, C by A of martensite increases with increasing carbon content. Why? Because the more and more carbon content, the probability of these places occupied by carbon is going to be more and more. So there is more and more difficulty in the shrinking to occur for the C axis, and that is the reason why C by A ratio does not decrease. Usually C by A ratio is in the range of 1.1 to 1.2 or something like that, 1.05 also people observe, depending on what is the carbon content. So some shrinkage will occur, but not all, and as a result this will not come to 1. When will this come to 1? When carbon is not there. That is why any of the iron based alloys where carbon is not there, then you can have a martensite which is a BCC martensite. it will be a soft martensite. All martensites need not be hard. BCT martensite is hard because of its structure and because of the strains associated with the shear. There is a strain associated with the shear even in BCC, that alone will give you a additional strengthening, but otherwise as such it is a BCC. It is martensite because it was formed by shear, that is it. What exactly causes? Because the atoms are not able to move, their atoms are not able to diffuse, and FCC is not stable at the temperature. So, it wants to finally come to a equilibrium shape, equilibrium structure, which is a BCC structure. It can come a normal pure iron. When you take a pure iron at high temperature above 910 it is FCC, below 910 it is BCC. How does this FCC to BCC transformation take place when I am cooling up from above 910 to below 910? How does the transformation occur? It is by short range diffusion. The atoms which are sitting at the body centered face centered positions move to body centered positions, and as a result you generate a BCC structure. From every one FCC unit cell you generate 2 BCC unit cells. Obviously there are 4 atoms, 4 lattice points per unit cell, here you have only 2 lattice points per unit cell. So, by this kind of atomic rearrangements in a short range, which is of the order of 1 unit cell dimension movement of atoms do not move beyond that, and that is what is a short range. But the same FCC, if I quench it to room temperature, the same pure iron FCC gamma iron I quench to room temperature, then this iron wants to become BCC because FCC is not stable at room temperature. It now forms a BCC by a shear. It first forms does a shear, then it gets converted to BCT, and this BCT, because there is no carbon atoms, because BCC is the stable structure not the BCT, it transforms to a BCC. So, ultimately the structure is BCC, but this BCC has been got by a shear process, that is why this BCC will be stronger than the original BCC which has been obtained by a normal cooling. So, by quenching a FCC pure iron you would get a strengthening, that martensite will be stronger than the original BCC iron, but it would not be as strong as a BCT martensite in a steels, understand. So, this is how you would see that. And for example, if I take iron nickel alloys also you see the same type of transformation taking place. No, in our iron carbon diagram, what is the low temperature stage? You remember the phase diagram? There is nothing like FCC is the stable state, depends on which particular electronic configuration of that element. For example, there are metals which are forming BCT, isn't it? There are so many, tin is a BCT structure, it is not even a cubic structure. So, different elements get different crystal structures depending on what their electronic configuration which allows it to have. If it allows it to have FCC, yes, we say that cubic is most popular. Among the cubic, some can be FCC, some can be BCC. One thing I want to tell you, FCC and BCC, the symmetry is the same. Whenever we talk of symmetry, we do not talk of symmetry of a unit cell, we talk of symmetry of a crystal system.
Sir, but entropy of BCC is more because of loose pipe, which is supposed to be stable at 9.
If you look at the entropy just based on loose packing, I do not think that is the right way of looking at it. Yeah, you can say that because it is loosely packed, okay, the heat capacity will be higher, could be higher, that much only I can say, because atoms can vibrate more easily.
Will that does it result to more entropy?
Need not, it will also result to higher enthalpy also integral Cp dt. So, it is not that yeah, to some extent there is more open space. So, but then the thing is, it is not more open space does not mean more disorder, is not it? It does not mean that you cannot say that BCC is more disordered than FCC. You cannot say that. It is as ordered as an FCC is in terms of atomic ordering. Yes, it is like, for example, liquid. Okay, that is where the problem is. In principle, that is why actually FCC again becomes BCC at higher temperature. FCC again becomes BCC. It is the magnetic transitions that are there in iron which make this happen, FCC to BCC to FCC, okay, and FCC again going to BCC. But there are structures where you would see, for example, if you take cobalt, cobalt is HCP at room temperature and becomes FCC at high temperature. But there are also examples where the HCP at low temperature becomes a BCC at high temperature. Titanium is an example. But there are also examples where it remains HCP up to the melting point. Magnesium, zinc is HCP up to melting point. So, it is these structural transitions are more fundamental issues. You need to look at what the actual issues related to magnetism, whether this material is ferromagnetic or not, that again influences to certain extent whether it ferromagnetic remaining or not. But in all these three, if you take nickel is FCC up to melting point, iron has a BCC to FCC to again BCC, cobalt you take it is HCP to FCC. So, all the three, though the three of them are ferromagnetic, they do not have the same type of structures. So, that means it is again because their electronic configurations are different. Could be, one electron can make copper and zinc, you see they are entirely different. It is also one electron, they are entirely different. So, it is more fundamental issue we need to understand. I do not think physicists also have understood this that well. We still do not know, I at least do not know still. Okay. Okay, come back. No, lattice positions do not, because that is what we say shear. So, shear basically means the one lattice structure changes to another lattice structure by a shear, that is it. And once that happens, that wherever lattice positions are there, this is what we call it as Bainite distortion. Okay, we will stop now.